Hello and welcome to lesson 4 of chapter 3, part 3, where we are going to be doing derivatives of logarithmic functions. So we've already taken a look at exponential functions with a base of e and how to find those derivatives. We've reviewed logarithmic log laws as well as looked at ln. So remember, ln is our natural logarithm, which is a log with base e. And in calculus, you're usually dealing with ln or exponential function with a base of e. Rarely are you dealing with other exponential functions or logs of other bases. So we're going to be doing mostly practice questions around ln. So if I want to differentiate ln, the first problem we have is we don't know how to derive ln yet. So our only option is to rewrite this as something we do know how to derive. And we know how to derive e. So just a reminder before we start, the derivative of e to the x is e to the x. And if you have some sort of function in your exponent, say some function u, then the derivative is e to the u times u prime, the derivative of the exponent. So chain rule applies if you have another exponent here. So what we're going to do is we're going to rewrite this ln x in exponential form. So all this is a logarithm with base e. Y equals ln x would be the same as e to the y equals x in logarithmic to exponential form, just changing the form of the equation. We haven't done any derivative yet. If I want to find the derivative, I would do the derivative of the left, and I would need to do the derivative of the right. Again, as you guys get going, you're not going to write this d dx each time. On the left, the derivative of e to the y is e to the y, and then we also need to do the derivative of the exponent. So we need implicit differentiation here. The derivative of y with respect to x is dy dx, or y prime, and the derivative of x is 1. If I rewrite this, I'm trying to find dy dx here. I get dy dx is equal to 1 over e to the y. But we know that e to the y is equal to x. So this is also equal to 1 over x. In other words, the derivative of ln x, derivative, is 1 over x. Again, chain rule would still apply. So if I have an actual function inside of the x, we would have one, or inside of the ln, we would have 1 over the inside stuff times the derivative of the inside. So if I look at question D here, we see we have something similar, but you have actual stuff inside of ln. So the outside function here is the ln, but you also have an inside function, which indicates chain rule is needed. Okay, so if I want to find y prime, the derivative of the ln portion is 1 over x squared, because you can see if you compare this to the previous question we did, instead of having an x, I have an x squared. So instead of having 1 over x, I'd have 1 over x squared here. And then chain rule says that we need to multiply this by the derivative of the inside function. Well, the derivative of my inside function would be 2x. Okay, so this here is the derivative of ln. And this here is the derivative of the inside. Okay. Now I can fix this up. I can rewrite this as 2x over x squared, or 2 over x. So you do not need to be able to reproduce all the work that I just showed in letter A, as long as you know the derivative of ln is 1 over x, or 1 over the inside stuff, times the derivative of the inside if necessary, chain rule. As long as you know this, you're good. Now for B, we want to find the derivative of some other base. Instead of e to the x, we have some other number a to the x. So a here is just any number. So for example, if you had y equals 3 to the x, or something like that, okay? Now the problem is, again, we don't know how to find the derivative yet. We know how to find the derivative of ln of something, and we know how to find the derivative of e to the x. So I can either try and rewrite this with a base of e, which, good luck, not possible really. It's possible, but not something we'd want to do. Or we can rewrite this as a ln. So if I ln both sides, then I can use my log laws to bring the exponent down. Now remember here, a is just a number, which means ln a is just a number. This is not a variable, okay? So if I find the derivative on the left, the derivative of ln is 1 over the inside stuff times the derivative of the inside stuff. The derivative of the inside would be by dx. On the right-hand side, you have the derivative of x, which is just 1. And ln a is just a number. It's a coefficient. So the derivative on the right is just ln a. Now, again, I'm trying to find dy dx. So if I rearrange, I get dy dx equals ln a times y. But I know the top, y is a to the x. So this is ln a times a to the x. So in other words, the derivative of a to the x is ln a times a to the x. We can follow similar logic with our next question. Again, a is just some number. So for example, this might be log base 4 of x. Again, we don't know how to do a derivative of log yet. We know how to do the derivative of ln. So one option would be to do change of base here. So you could rewrite this as y equals ln x over ln a. That would work. And then this is the same as saying 1 over ln a times ln x. And this here is just a number. So then if I were to do y prime would be 1 over ln a, because that's just a number, something like 5 or 2, right? That's just a number, times, and then your derivative of ln x is 1 over x. Or you could rewrite this as 1 over x ln a. Okay, so one option would be to do change of base. Another option would be to rewrite this in exponential form. We'd have a to the y equals x. And then we can find the derivative of both sides here. The derivative of a to the y is ln a times a to the y, and the derivative of x is 1. Okay. Now on the left, I forgot to do the derivative of the exponent. The derivative of the exponent, should be dy dx. So I should be including that on the left and deriving variable. I'm trying to get dy dx by itself. So I have dy dx equals 1 over ln a times a to the y. But again, we rearranged up here, and a to the y is equal to x. So I get 1 over ln a times x. So I get the same answer. So it kind of depends on what you're comfortable with for this one. You can either do change of base or you can rewrite in exponential form. But again, really what you need to know is that the derivative of log base a, some number a of x, is 1 over x ln a. So the example I gave was log base 4 of x. So y prime for this question would be 1 over x ln 4. Okay. Again, if you had stuff inside the log, you would need chain rule and you would need to multiply by the derivative of the inside stuff. And these are all on the bottom of your page here. So you don't need to memorize these. A, B, and C are just so you know where it comes from and you're not just taking my word for it. Okay. So these are all the rules at the bottom here. Have those handy when you're doing your questions. Okay. So the last one we haven't taken a look at yet is this one here, which we're going to look at in E. So we're going to break this into two cases. So remember that for the absolute value of x is equal to x if x is bigger than 0, and negative x if x is less than 0, which we reviewed in chapter 0 and chapter 1. So we're going to break this into two cases. So y equals ln absolute value of x is actually equal to ln x. X is bigger than 0, and therefore y prime would be 1 over x. Okay. Y is equal to ln x is equal to ln of negative x if x is less than 0, because absolute value is negative x if x is less than 0. Now, if I find y prime, I'm going to have 1 over negative x, because that's the inside stuff of my ln, and I would need chain rule here. I need to multiply by the derivative of the inside, and the derivative of the inside stuff is negative 1. And so those negatives will cancel out here, the negative 1 on the top and the negative on the bottom. We end up with 1 over x as well. Okay, so therefore, y equals ln absolute value of x, y prime is 1 over x. And that's what we have. So A, B, C, and E are just showing you why these derivatives are what they are, so that you're not just, again, taking my word for it. You can actually see where they come from. D was the only one that's a new example. Just reminder that chain rule does apply. Okay. Again, this one's going to be the one that you're going to see the most here. This one right here. Okay. Now, there's one other thing in this section, which is called logarithmic differentiation. So if I see something like this looks absolutely disgusting. Right now, our way of finding the derivative here would be some sort of product rule. But the problem is I have three things that I'm multiplying together. What that means is, let's say this was F, this was G, and this was H. Don't write this down. I'm going to erase this in a moment. If I wanted to use product rule, I would have to do F prime times G times H plus G prime times F times H plus H prime times F times G. And then I would still need to expand and simplify. I wouldn't be able to leave it like that. Okay. So this would be completely huge and disgusting. Right. So instead of doing something awful like this, I can use something called logarithmic differentiation, and we use this on problems that have multiple products, quotients, and also have some exponents. What I'm going to do is I'm going to use logarithms, specifically ln, because of this e here. Okay, because of this e, I'm going to use ln, and I'm going to use this to be able to split this equation up and simplify it a little bit before I find my derivatives. So notation is very key. As you guys have been going through the different chapters and submitting your work, some people are not being clear about when they're dealing with y versus y prime. So this matters. If you have a picky professor in university, they'll give you 0 marks. They assume you don't know the difference. Okay. What we have here is y. As we start this question, we're still dealing with y. Only once we start using our derivative would we ever use y prime. So you need to be very clear about whether you're dealing with the original function or the derivative. Okay. So what I'm going to do is I'm going to log both sides so that I can split up the right-hand side using log laws. I'm going to use ln specifically because of that e. Okay. So if I log the left using ln, I'd have ln y. And if I log the right using ln, I have root x times e to the x squared times x squared plus 1 to the power of 10. Now, log laws say if I have things that are multiplying together inside the log, I can split that up by addition. So I'm going to rewrite this as ln of root x, but I'm going to, in the same step, just change that to an exponent, plus ln of e to the x squared plus ln of x squared plus 1 to the power of 10. Now, again, using log laws, my power law says that if I have an exponent, I'm allowed to bring that down in front of the ln as long as the exponent is applying to everything that's inside of the ln. So I'm allowed to bring down this exponent here. The entire x squared will come down because that is the exponent on the inside stuff. And this 10 can come down. I cannot bring the 2 inside here. This 2 cannot come down because it is not applying to everything inside of the ln. It's only applying to part of it. So once I do that, I'm going to have 1/2 ln x plus x squared ln e plus 10 ln x squared plus 1. Now, I also know that ln e is equal to 1, so I can get rid of that ln e because x squared times ln e is the same as x squared times 1. I cannot simplify this at all. That does not simplify. And all this time, the left-hand side, I've done nothing. It is still ln y. Okay? So step 1 here was to ln both sides. Step 2 was to use log laws to separate all of this stuff. And this is so that when we proceed with our derivative in our next step, we're going to have a much easier time. So I'm going to choose to rewrite this just one more time with this middle term on the right, just looking exactly nice and neat and perfect so that when we do our derivative, it's a little bit less messy. So now if I do the derivative on the left, the derivative on the left would be 1 over y times dy dx, because the derivative of y with respect to x is dy dx from our implicit differentiation last chapter. And here we could use y prime instead if you don't like dy dx. It's fine. Sorry, next. On the right, the derivative of the first term, the half would stay. It's a coefficient. It's just going to stay there. Derivative of ln x is 1 over x. The derivative of x squared is 2x. Again, the last term here, the 10 is a coefficient. It's just going to stay. The derivative of ln is 1 over x squared plus 1. That's our inside stuff. And we will need chain rule for this one. The derivative of the inside function, the inside stuff, would be 2x. Now, again, I'm going to choose to rewrite this just so that it's not quite so messy. So this is going to become 1 over 2x plus 2x plus 20x over x squared plus 1. If you want, you can choose to make a common denominator here and write this as one giant fraction. You do not need to do that. You may leave it like this for these questions specifically if you would like. Okay. So on the left, I still have 1 over y times dy dx. Now my job was to find dy dx, find my derivative, so I need to move the y to the other side. So I have 1 over 2x plus 2x plus 20x over x squared plus 1 times y. Now, again, you should not be leaving y here. You need to plug the original y from the question back in. So my original y from the question was root x times e to the x squared times x squared plus 1 to the power of 10. You may leave this here if you would like. If you really wanted to expand and simplify, you could, but it's going to be worse, not better. So really, if you're not leaving it like this, the only other way your answer should be is if you chose to make common denominators in this first set of brackets and then cancel some of the denominator stuff out with this second set of brackets. So online, I've shown on the PDF that I've posted, the answer key, I have shown what that final answer would look like. So what would happen if I made common denominators in the square brackets and made this one giant fraction? And therefore what it would simplify to once you cancel some of that out with my y here in the round brackets. But you do not have to do that. So you may leave it here if you want. Okay, so step 3, what we did is we actually found dy dx. Okay, that's what we did. And then here we isolated dy dx. And then our last step is to replace the y with the equation given in the question. So if there are multiple fractions or multiple multiplications, and you also have some exponents in there that you would need to find derivatives of, you can log both sides and split it up and then derive. Okay. There are a lot of questions given to you here at the bottom of practice. You do not need to do them all. Pick some and try them. If you are having trouble with the basic ones, I would do a couple of those first. If you're like, the basic ones are fine, I want to do some hard chain rule questions, do those. If you are fine with the chain rule type questions, then try the logarithmic differentiation questions. But there are way, way, way more questions given to you on the bottom of this page here. As you can see, you do not need to do all these. This is a lot. But if you are finding that you're having an easier time, pick some of the harder ones. If you're having a harder time, pick some of the more simple questions to try. And that would be your chapter 3, part 3, unless you are choosing to move on and try lesson 5.